Welcome everybody to this meeting of our colloquium, Quantum Contextuality in Quantum Mechanics and Beyond. It's my pleasure to announce that today's speaker is Paweł Kurzyński of Mickiewicz University, and he will be telling us something about the limits of contextuality. So, Paweł?
Thank you very much, Lekti, and thank you. Big thanks to all of you that you are here. Okay, so let me go straight to the point. What I will talk about. So, as the title suggests, I'm going to talk about some limits of contextuality, and the reason why I'm interested in this limits of contextuality is because I'm interested in this. I think one of the most fundamental questions is that why we do not observe contextuality and non-locality in world around us. And to be more precise, because I know that FT is studying contextuality, but not exactly quantum contextuality. So the thing is, why we do not observe quantum contextuality in the surrounding universe. And maybe just initially, let me say something about my language. So we know that non-locality is a special case of contextuality, but here in my talk, when I'm going to speak of non-locality, I'm going to think about spatially separated systems we know very well. So basically Bell's scenarios. And actually here I'll speak of CHSH inequality, but all these things can be of course, these things also apply to other scenarios. And when I will talk about contextuality, I will mean local systems. So I will talk here about this Kryashko-Kant-Szumowski inequality, this KCBS scenario. But of course, again, these results can be considered in other scenarios. So this problem of macroscopic contextuality is related to the following things. So basically, initially, I would like to define or introduce you to two problems. The first one is the problem of what is really macroscopic, how we define macroscopic, or more precisely, how we define macroscopic measurements, because contextuality is about measurements. And the second problem is about indistinguishability, because this macroscopic measurements suffer indistinguishability, and there are two types of indistinguishability. At least I like to divide indistinguishability into types. One that I call fundamental, and another one that I call effective. So I will just tell you what it is. And then once I introduce this, I'm going to show you that basically these problems are extremely related to these limits of contextuality, namely monogamy bounds, monogamy of non-classical correlations. And the other thing is exactly this problem of indistinguishability. So I'm going to tell you what are the implications on contextuality of this. And already let me just tell you what are the main results. Basically, when we are talking about Bell, Cauchy-Specker inequalities, we consider some function of measurements that can be performed in laboratory. And then we calculate an average value of this function. And then we use this hidden variable theory, either local realistic or non-contextual hidden variable theory, to divide this upper bound on this function, on this average value of this function. This is what I'm going to call this CHV. And then in quantum systems, or in general non-classical systems, the average value of this function can be larger than this, and this is violation. So this is something that we know very well, but just I would like to briefly state it right now. Okay, so we will have violation if this quantum value CQ is larger than this hidden variable value CHV. And then so what I'm going to show is that in case of macroscopic non-locality, this value, this quantum value calculated on these macroscopic samples is going to be less than this classical hidden variable value. Interestingly, in contextuality, in local scenarios, the situation is slightly bit different. This quantum value will not change with the size of the sample, but what's going to change is going to be this hidden variable bound, this CHV. In the macroscopic limit, it's going to change, it's be bigger, and therefore there'll be no violation. Okay, but before I start, let me also tell you that the thing that I'm going to talk about will be, of course, related to some of my work, and this is work that that was not done solely by me, of course. So a lot of this research results from my long-time collaboration with my friend Dak Kaszlikowski from Singapore. And then there are also plenty of other people involved. So for example, my research on monogamy and of locality and contextuality was done with Ravi Ramanathan, who's now in Hong Kong, Tomek Płaterek and Wiesiu Laskowski, they are in Poland, Alistair Kay, he's in UK right now, Aki Soeda in Japan, and Alan Cabello in Spain. And then about indistinguishability contextuality, that's the topic that I was investigating together with my friends from Poland, with Marcin Markiewicz, Antek Wójcik, and Marcin Kaczewski. Okay, so let me go to the general scenarios that I'm going to consider. First, let's look at this first, this top left and the top right picture. So in case of contextuality, again, here I mean local systems, what we have is just a single system. And this, we can ask different questions to the system. A question A, so we perform a measurement A, we can choose to perform another measurement B, C, D, and so on up to Z. And then in the end, after performing many repetitions of these experiments, we evaluate in our laboratory the average values of A and so on. In case of non-locality, we basically have 2 copies or even more, but again, as I said, I'm going to focus on the CHSH scenario. Or in general on bipartite scenarios. So we have 2 systems, and Alice on one side can ask these individual questions A1 to Z1 to her system, and Bob will ask another questions, and then in the end they will calculate this correlation. So basically A1 A2, A1 B2, and so on. All possible correlations between them. Now, if we go to the macroscopic limit, we will deal with many systems. So we will have n systems. And right now we will ask collective questions to these systems. Okay, like for example, right now we can ask a question A to this particle, we can ask a question A to this particle, and so on. We can ask also different questions B, C, and so on. But the important thing is the limitation. So by meaning that we are in the macroscopic limit, I mean that we are unable to address individual particles. We need to address them collectively. So it means that if I ask a question A to this particle, I need to ask question A to all particles. I cannot ask question A to one particle and question B to another particle. That's the idea. Because if I'm doing so, it means that I'm already somehow at the macroscopic level, so I can distinguish between these 2 particles. Which means that in the end, I basically am going to consider only some special types of questions, special types of observables, a sum of all possible questions of the same type to all systems. And the sum is also important because apart from the fact that I need to address all particles collectively, I cannot get answers from these particles individually. What I need to have is that I get some collective answer that does not allow me to recognize which answer comes from which particle. So that's why basically we need to lose, we need to abandon this distinguishability simply by summing. In a moment, I'll just give you some nice intuitive example. And then the case of non-locality is similar to this one. So this time we have 2 systems. There might be some non-classical correlations and extremely complicated non-classical correlations between these 2 systems. So I'm not saying that this huge system is classical. It might be non-classical, but right now we can only ask these collective answers on the Alice side, collective answers on the Bob side. Collective questions on Alice side, collective questions on Bob's side. And in the end, we can only calculate the average values of this type. So for example, all possible questions A on this side with all possible questions Z, for example, on this side. So we need to consider all possible pairs of questions. All right, so now let me maybe define, let me be more precise about what I mean by a macroscopic measurement. So first, let's say that we have a single system, and for the system we can define this question A, which is basically this kind of observable. So I'm already within the quantum formalism right now. This is how I define this operator A. And then imagine that I have right now n copies of this system. So I need to define what I mean by asking A asking nth particle question A. It basically means that I define this operator AN. I have this tensor structure of my Hilbert space. So basically this operator A is at nth position, and on all the other positions there is identity. It's a clear thing, I hope. And then collective observable is basically defined as a sum over all these ANs, sum over all n particles. And again, as I said, macroscopic measurements cannot reveal individual outcomes. And let me just give you a simple example. Let's say that we are interested in magnetization of some huge number of spin half particles. So in this case, this observable A is some spin observable with outcomes +1/2 and -1/2. And right now, this total collective magnetization observable has n+1 outcomes that have these values from -n/2 up to n/2. And what is also interesting here is that right now the number of outcomes is linear in the number of particles. Whereas if we really have n spins, the total number of microscopic outcomes is of course 2 to the power n. So by going to this macroscopic limit, we basically lose a lot of information. We don't get all, we just lose this huge exponential number. We just change it into this linear in n number. But actually this is also too much, because what if n is an Avogadro number, 10 to the power 23? It's also a huge number of outcomes. So in fact, in reality, when what I mean by macroscopic measurements is basically a measurement of average values of these collective observables. So we get average values, not exact outcomes. And again, here I would like to say that the scenarios and such defined macroscopic measurements were considered by many people. So I'm going to present during my presentation. I'm going to show you some references, and of course, it's a very subjective selection. So I apologize everyone who's not cited, but these are the works that influenced me, and these are the works to which I contributed. So these scenarios were considered in this paper, but there are of course many other papers that consider such problems, such scenarios. Okay, and now having defined macroscopic measurements or collective measurements, I'm going to show you that they have some important property related to indistinguishability. So first, let me quickly say what I mean by indistinguishability. Usually, when physicists speak of indistinguishability, we mean indistinguishable particles, which is something that I call fundamental indistinguishability. So basically, if I have a state of n particles, and it's described and it's given by some density matrix rho. So if these particles are identical, then the state will not change if I swap some particles, if I perform any permutation of particles. These states are permutationally invariant, which means that basically rho will be equal to rho after any permutation. Okay. Now, let's say that in principle, we have a system which is made of distinguishable particles. Then of course, rho does not need to be symmetric. Moreover, even let's say that it's made of indistinguishable particles, but these particles can be labeled by some additional degree of freedom. So in principle, they can be distinguished, like for example, a position on a lattice. So such a state is no longer permutationally invariant. So if we perform a permutation, we'll obtain a different state. But now, despite the fact that our state, the state of our system may not be permutationally invariant, our collective observables are permutationally invariant. So basically, if we apply any permutation on this observable, we will obtain the same observable, which means that basically if we evaluate this collective observable on our state rho, it is equivalent to evaluating our observable on the state rho after symmetrization. So basically we obtain this effective symmetrized state by basically taking this rho and applying all possible permutations of particles and averaging over this permutation. So you see that this state must change drastically. Plenty of things will be averaged in this state. And the question is whether any non-local or non-classical properties, will they vanish or not? So the important question is right now, does this state rho effective exhibits any contextuality? Okay, so for a moment, let me right now leave this macroscopic considerations and go to the microscopic scale. Because I would like to speak of monogamy of Bell inequalities, and in a moment you're going to see that this monogamy is actually very, is extremely related to this problem of macroscopic measurements. So right now, imagine that there are only 3 particles. Let's say one particle that belongs to Alice, another particle that belongs to Bob, and the third particle that belongs to Charlie. And each of them can perform one of 2 measurements on the particles. So you already see that it starts to resemble the CHSH scenario. Alice can perform A1 or A2, Bob B1, B2, and Charlie C1 or C2. And again, these measurements are ±1 measurements. So standard CHSH scenario, I will not go into details because you know it very well. And right now they are going to consider 2 CHSH scenarios. So the first one is the CHSH scenario. So basically they evaluate the following thing. It's the CHSH scenario between Alice and Bob, and another one is a CHSH scenario between Alice and Charlie. What is very important, and please keep in mind that in both scenarios, it's the same measurement of Alice here and the same measurement of Alice here, the same A2 here and the same A2 here. So basically, how it may look like. Alice performs her measurements, so she has a table of data. Bob performs his measurement, he's got a table of data, and then Charlie performs his measurements and gets his own table of data. And then in the end, either Alice and Bob meet and try to figure out this value, or Alice and Charlie meet and try to figure out this value. And the question is the following: can they both violate Bell inequality, violate the CHSH inequality? So is it possible that both of these are greater than 2? And again, as I said, there is a number of papers that study this problem, and as far as I know, this is the correct historical order here. All right. So how this scenario looks like? So again, in general, we have these 3 systems, 3 particles, A, B, and C. And the total state of these 3 particles, this rho A, B, C, can be very complicated. There might be some interesting tripartite correlations in the system, but in the end, we are only interested in bipartite correlations, correlations between A and B, and correlations between A and C. And right now, I plotted you some graphs. These graphs represent all possible measurements in our system, and this connection, these links, corresponds to joint measurability. So what you can see, for example, here, you can jointly measure A1 and B1, okay, because they are connected. You can measure jointly B1 and A2 and so on. And you see that different colors corresponds to different CHSH scenarios. Like for example, this red links correspond to the CHSH scenario between Alice and Bob, whereas these green links here correspond to the CHSH scenario between Alice and Charlie. There are also these blue links that corresponds to some CHSH scenario between Bob and Charlie, but well, I mean, we do not consider it here, but nevertheless, such scenario can be considered. And the important thing, the very important thing is that you can consider some loops. And for certain loops, there'll be some diagonal links in the middle, and these diagonal links will be important. So, okay, if you consider loops of the same color, you have standard scenarios, but you can consider loops of mixed color. If you consider loops of mixed color, like for example, a loop consisting of both A's, but here we have B1 and C2 here, due to joint measurability of B and C, there'll be this inner link here. The same thing here. And this is important because this allows us to derive the so-called non-signaling monogamy bound. So first, let me state it, and then in a moment, I'm quickly going to prove it. So the non-signaling monogamy tells us that the CHSH value between Alice and Bob plus the CHSH value between Alice and Charlie must be bounded by 4. And we know that the violation occurs when this value is greater than 2. So if CHSH is greater than 2, due to this bound, this CHSH AC must be less than 2. and vice versa. If CHSH-AC is greater than 2, then CHSH-AB must be less than 2. So you see that at most there is one violation. Only one pair can violate CHSH inequality. And how to prove it? And the crucial thing is the following observation, that actually the sum of these two expressions can be rearranged. So each expression is a sum of 4 correlations. Maybe let me go back here. And these, the first scenario corresponds to this loop here, this red loop. The second scenario corresponds to the green loop, but we can rearrange them such that we will obtain this loop here and this loop here with this additional diagonal in the middle. Okay, and because, so this is what I call this CHSH prime AB and CHSH prime AC expression. And right now you see that because of this links in the middle, because of this blue connection, there cannot, this CHSH prime expressions cannot be violated, simply because for these expressions there is a joint probability distribution. You can find a joint probability distribution P A1, A2, B1, C2, simply because this can be measured in laboratory, this can be measured in laboratory. The same thing for the other one. So we know that definitely this is bounded by 2, this is bounded by 2, so in total everything is bounded by 4. So this is how we obtain this monogamy. Maybe just one comment. This is called non-signaling monogamy because there might be tighter monogamies that can be derived within quantum theory, and I'm not going to talk about them in this talk. But so I'm going only to talk about this non-signaling bounds, and why do we call them non-signaling? So I just give you a simple example. Imagine that we are even outside of quantum theory, and we are dealing with PR boxes. So what if both violation of CHSH inequality between A and B is equal to 4, and there's also a violation between A and C, and it's equal to 4. This means that all of these correlations are equal here to 1, the last one is equal to -1. The same thing in Alice-Charlie scenario. All of them are correlated, the last one is anti-correlated. And then imagine what would happen if Bob and Charlie were actually collaborating. So let's say that they are not spatially separated, they sit in the same laboratory and they can compare their tables immediately, and their data immediately. So you see here a very interesting thing. So imagine that Bob will only be interested in B1 and Charlie will be interested in C2. And let's say that Alice measures A1. But you see that if Alice measures A1, we know that A1 and B1 are correlated. And A1 and C2 are correlated. So it means that B1 has the same value as A1 and C2 has the same value as A1, which means that B1 and C2 must be also correlated. So this must be equal to 1. So if Alice measures A1, they will observe perfect correlation. But here right now, let's say that Alice, still Bob and Charlie are observing the same thing. The only thing that changes is that Alice right now decides to measure A2. So this is something that happens in Alice's laboratory. And right now, we know that B1 and A2 are correlated, so they have the same value, but C2 and A2 are anti-correlated, they have different value. This means that B1 and C2 must also be anti-correlated. So if Alice measures A2, then Bob and Charlie observes anti-correlation. So if they decide to basically to collaborate, and they will decide that Bob will always observe B1 and Charlie will always observe C2, then by observing that suddenly they have correlation or anti-correlations, by doing so, they will basically receive signals from Alice, because Alice can signal to them by simply changing her setting. Okay, so this is a very strong property. We know that non-signaling is not allowed. I mean, at least this is all the facts say so, that non-signaling is, that superluminal signaling, instantaneous signaling is not possible in our universe. That's why such a bound needs to apply in our universe. All right. Now, how to apply this thing to the problem of macroscopic locality? So right now we go again to many particles. So imagine that Alice has n particles and Bob has n particles. Our monogamy bounds say that basically the violation of CHSH inequalities can only happen between a certain pair of particles. So at most, in the system, at most n pairs of particles can violate the CHSH inequality. There is some.
Paweł, if you can hear me, there is some kind of noise now in the background.
Okay, I think there is no noise.
Okay, now it's fine.
Thank you. Thanks for that. Okay, so again, as I said, we have n systems at Ali's side, n systems at Bob's side, and due to monogamy, we know that only certain pairs can violate CHSH inequality. So among all possible n square pairs, only n of them will violate CHSH inequality. The remaining pairs cannot violate CHSH inequality. So if we randomly choose some pair, it's highly unlikely that we will find a pair that will violate CHSH inequality. And right now, let's recall that in our collective measurement scenarios, so in our macroscopic limit, we simply cannot say which particle is which. Therefore, we basically need to average over all possible n square pairs. So we see that this locality needs to get somehow diluted. So I'm going to show you an example that already works at the 3-particle scale. So imagine that Alice has only one particle, A, and Bob has these two systems, 2 particles, B and C. And Bob cannot distinguish between B and C. So the whole system is a tripartite system, rho ABC, just like the one that we were discussing during when I was introducing this monogamy scenario. And now Bob effectively is not allowed to distinguish between B and C. So in fact, he measures collective observables. So B1 plus C1 or B2 plus C2, and we call them D1 and D2. And then again, so if we want to plug them into CHSH scenario, we need to normalize them to +1 and -1. They will also, actually, interesting thing, they will have also value 0. But then still, we can consider a CHSH scenario. And then if you plug this D1 to this CHSH scenario, you will see that this actually is equivalent to the CHSH AB plus CHSH AC. But this is bounded by 4. And since we need to average over this, we need to divide by 2. We see that this averaged Bell inequality, or this macroscopic, so-called macroscopic Bell inequality, can never be violated, because this value can be at most 2 due to this non-signaling bound. Okay, and now I want to show you something. I mean, I'm still going to talk about this scenario, but I would like to show you some other property. Not only that this macroscopic correlations do not violate CHSH inequality, but also that for this macroscopic averages, there exists a joint probability distribution that explains them. And in order to do so, I'm going to apply the following 4 steps. So basically, initially, we start with the following system that consists of many, many particles, and we divide it into 2 parts. So there'll be Alice part, which is denoted by this black particles, and there is Bob's part, which consists of these red particles. And in principle, these particles are distinguishable, so that's why I can enumerate them. And this system can be correlated in an extremely complicated way. So there might be very interesting non-classical correlations between them. But now, the problem is that since we can only perform collective measurements, Alice can perform collective measurements and Bob can perform collective measurements, we need to lose this distinguishability. So we need to symmetrize over all, we need to perform all possible permutations at Alice's side and Bob's side. So we lose identity of particles. And because of that, each pair of such particles is right now described by exactly the same density matrix. So this is basically what we do. This is this dilution procedure that I mentioned. So effectively, you see that this system starts to be describable by only a pair of particles. So again, because of macroscopic limit, this system is macroscopically equivalent actually to a pair of particles. And you see that this pair of particles must be somehow weakly entangled. Okay. So again, the problem is the following. We have these macroscopic correlations, let's say this calligraphic AI and BJ, and we ask whether they stem from some joint probability distribution. Can we find some joint probability distribution that will properly give us such correlations? So again, first observe the following thing, that Alice has, as we said, Alice has n copies and Bob has n copies. So these correlations can be defined in the following way. So this is this first collective observable, another collective observable. And actually the summations can be taken out of this average. So it's the sum over all possible n square pairs of questions, A to nth particle at Ali's side and question B to nth particle at Bob's side. And so we sum over n and m. All right, and now we know that due to effective indistinguishability, so due to the fact that these collective observables are symmetric under permutations, evaluating this on our state rho is equivalent to evaluating this average value on this effective state rho, which is this original state, and we take average over all possible permutation on Ali's side and Bob's side. And now we know that for such system, for such symmetrized state, all bipartite states between Alice and Bob, so if we calculate a reduced density matrix, are exactly the same. So if you evaluate this once more, you see that basically this correlation is equal to n squared times this effective bipartite correlation. Okay, and now what I want to show you is that this effective bipartite correlation actually admit a joint probability distribution. So how is it possible? So instead actually of 2 particles out of this two n particles, we choose 4 particles. So let's say that we choose 2 particles at Ali's side and 2 particles at Bob's side. Due to this effective symmetrization, we know that this pair here is described by this rho effective state, this pair here is described by this bipartite rho effective state, and so on. All possible pairs are described by the same state. And although I said that in our laboratory, the macroscopicity tells us that we need to address this particle and this particle with the same question, and the same thing for Bob. Bob needs to address both particles with the same question, but in principle, it's possible that we ask this particle question A1, this particle question A2, this particle question B1, and this particle question B2. So in this case, by doing so, we obtain a joint probability distribution PA1, A2, B1, B2. Okay, this is actually something related to this. It's not even something related. It's exactly the idea of the symmetric extension that was studied in this paper here by Barbara Terhal and others. So again, we have a four-partite system, 4-partite subensemble. We ask all questions that are relevant for our scenario, because we can do it, no problem, because each question is asked on a different particle. And then we have this very nice property, namely that if we trace out this particle and this particle, we'll obtain exactly this effective bipartite state between these 2 particles, and we will obtain exactly our effective correlation that we want to have. So basically, from this joint probability distribution, we will obtain all observable correlations, which means that this joint probability distribution exactly recovers these correlations, which means that there'll be no, the system behaves classically. So again, what's a very important thing here, when it comes to macroscopic averages on macroscopic measurements, basically everything is describable by this 4-partite system, or more precisely, everything is describable by, all the correlations are describable by such a bipartite systems, but the joint probability of such a bipartite system can be calculated if we use this. We have, in principle, I mean, in general, we'll have Avogadro number of particles on Alice side and Avogadro number of particles on Bob side. So definitely there'll be such 4 particles. All right. So now let me go to the local scenario. So I'll go to contextuality, and let's see if similar things that I was discussing right now apply to contextuality. Again, maybe first, let me just summarize this non-locality scenario. So we see that basically non-locality vanishes due to this symmetrization, due to this effective symmetrization, because the original correlations are no longer measured. This state is completely different. So the question is, will we observe exactly the same thing in case of contextuality? And the answer is no. So what I'm going to consider again is this KCBS scenario, as I said before. And this KCBS scenario consists of 5 measurements. This is something that we know very well, so let me just briefly go through it. So we have 5 questions, 5 pairwise, always cyclically exclusive questions, cyclically exclusive events that in quantum theory will be represented by 5 cyclically orthogonal projectors. Okay, so we call them A, B, C, D, E, and this cyclic orthogonality means that A times B is 0, B times C is 0, C times D, and so on. Everything is 0. And then we have this KCBS inequality, or actually more precisely, is right inequality. So the averages of these projectors, actually the probabilities of these events, when we sum them and consider a hidden variable, non-contextual hidden variable theory, this sum must be bounded by 2. But we know that in quantum theory, we can reach up to square root of 5, which is like 2.23. Okay, so we can observe a violation. But right, the question, what happens if instead of a single system, we right now consider a collection of systems and perform the scenario on a collection of systems using collective observables and the following collective observables. So right now, we will not ask question A to one particle, but we will ask question A to all particles, question B, and so on, up to question E, defined for all particles, this collective question. And now, in the case of non-locality, we observe that this effective symmetrization actually destroys everything, whereas right now, this is not going to happen. Why? Because we can, when we speak of questions asked to individual systems, we can consider individual systems actually in a product state. Okay, there is no need for correlations. So we can consider n systems in the same state, in a product state. This is actually quite a physical assumption, because we can think of systems that do not interact, like photons, and they can be prepared in the same state. So it's not a problem. Okay, and now if we try to symmetrize them, of course, such a product is symmetric. So this effective state is going to be the same as the original state. So nothing happens due to this effective symmetrization, which means that average values of these collective observables are equal to n times average values of single particle observables without any symmetrization. I mean, nothing is spoiled by this symmetrization. Okay. So now you see that we are dealing with the following problem. That actually, on one hand, we can take each of these particles individually, and we can perform n tests of contextuality with a single particle, or we can treat them collectively in a single test, but done on n particles at the same time. And the question is it the same or not? Because if it's really the same, and we know that one system shows contextuality, it means that the other system also shows contextuality. We have contextuality on a macroscopic scale, which would be great. And such an example, and such a system again is the system that I mentioned. We can consider n photons. So we can consider a simple problem as one test on n photons or n tests on a single photon. Okay, and again, these problems were considered before. So here is, as far as I know, the correct historical list of such problems, and recently there have been more and more papers on it. Okay, so what I'm going to show you is that actually for more particles there will be no contextuality, but the reason is not that we will observe a change in the observable things in our laboratory, but rather something is changing at the level of the hidden variable models. So let's check what's going on with the hidden variable models when we consider different numbers of particles. So if we are dealing with a single particle, this bound is derived using this exclusivity assumption. This exclusivity assumption tells us that a particle can occupy at most one of two exclusive events at a time. So it means that if we assign a particle, for example, to event A, we cannot assign a particle to event B and event E. Okay, and already we see that this cyclic structures tell us that we can assign particle to at most two events. That's why the bound is 2. But right now, imagine that we have two particles. First, imagine that these two particles are distinguishable. So in this case, we have actually two different hidden variables models because we can consider a hidden variable model for each particle independently, or maybe, let's be more precise, not a hidden variable model, but rather two different assignments. One assignment will be done with black color, another with the red color. So the first particle can be assigned to event A and event C. The second particle can be assigned to event B and event D. But since we can distinguish them, we can basically calculate bound for each particle independently. Now the situation changes if these particles are distinguishable. So imagine for a moment that you get color blind and you cannot distinguish black from red. So you do not know whether this one corresponds to the first particle or whether it corresponds to the second particle, and so on. So we need to define some new type of exclusivity assumption. So first, maybe think about for a moment what can happen if you have two events and you have two indistinguishable particles. In this case, all exclusive outcomes that we can find are the following. Either two particles are assigned to the first to the first event, or two particles are assigned to the second event, or one particle is assigned to first event, one particle is assigned to the second event, but we do not know which is which. And that's the important thing. So basically, right now, you see that it can be easily generalized to the concept of n particles, and we come up with the following exclusivity assumption. We see that as we go from one particle to n particles, the exclusivity assumption right now becomes that two exclusive events can be occupied by at most n particles. And right now we have on all possible n+1 distributions, n particle on one side, 0 on another, n-1 on left and 1 on the right, and so on. Okay. And so right now, what will happen if we will go to laboratory? We will consider scenarios in which we deal with n particles. We will use detectors that will not distinguish between particles. So right now, basically, what we are going to observe the thing that we are going to observe will be average numbers of particles, basically. So basically, this A tells us what is the average number of particles, what is the intensity at detector A, okay? And then we can define probabilities in the following ways. This intensity at detector A divided by the whole number of particles. And you already see that because of this here, that if we divide it by n, we will get exactly the same value as we would get for a single particle. So we get the same probabilities no matter how many particles we have in our system, which means that this KCBS expression evaluated for n particles will be always square root of 5, no matter, I mean, assuming that we prepared it in this optimal state, but it will be always square root of 5, no matter how many particles we have in the system. But right now, what's going to happen is that this upper bound, this non-contextual hidden variable bound, is going to change with n. It depends on n because simply we can define this non-contextual hidden variable bound as a sum over all occupation, this hidden variable occupation assignments of particles to events with respect to our exclusivity assignments. So for example, if A and B are exclusive events, then NA plus NB must be less than n. Okay, and we of course need to maximize over all possible assignments. So you already see the following thing that, okay, if you have one particle, then of course this hidden variable bound is 2. If you have 3 particles, you see that you can have the following assignment. You can assign 2 particles to A, 1 particle to B, 2 particles to C, 1 to D, 1 to E. And it's okay with our exclusivity condition, simply because you see that the sums of over two connected vertices never exceeds 3. Okay, so if we sum all of these numbers together, we will obtain 7. Divided by 3, we'll obtain 2.33, which is already greater than square root of 5. So in this case, there is no violation. In general, if we go with n to infinity, or even if we consider some even number of particles, we can assign n-half particles to every event. Okay, which means that if we sum all of this together and divide by n, we obtain the bound of 2.5, which is quite interesting because this is this bound in generalized probabilistic theories, like in this PR box theories. So again, the conclusion is the following: that for one particle, you have contextuality because this bound, this non-contextual hidden variable bound, is less than value that we can measure in laboratories, less than square root of 5. But for more particles, we cannot violate it because this bound will be always greater. Okay, so let me summarize everything what I said. This is like the message that I would like you to take home. So the first thing is that when we study this non-local scenarios, or in general bipartite scenarios, this collective bipartite non-classical correlations will change as n changes, simply because of this property. But in case of single particles, in case of local scenarios, single particle probabilities, unlike correlations, they do not change. So single particle probabilities or intensities, they do not change. They are independent of n. But what is important, this contextuality bound changes, especially as n goes to infinity. All right, thank you very much.
Well, thank you very much, Paweł.